All right, so let's see here. Last time we talked about time series, right? I think we were going into the modeling and stuff like that. So we're going to kind of finish it up a little bit today, right? But once we finish time series, we'll actually go into neural networks, which is actually section 40. So we're actually skipping section 39, which if I remember right, 39 was natural language processing, NLP. Is that right? Yeah, and part of the reason why is because then we can talk about word embeddings in the context of neural networks, since that can be really useful. Natural language processing doesn't necessarily rely on deep learning, but understanding a little bit of like what you can do with deep learning, it makes a little bit, I think it makes it a little easier to understand what you can do with NLP in that deep learning context. So that's kind of the reasoning for it. So just give me a thumbs up. Has anyone touched section 40 already? Just give me a thumbs up if you at least like opened it up and started looking at it. Okay, see a couple of thumbs up. Okay, maybe see a couple people kind of shake their heads or not raise up, so that's okay. So one thing I'll say is that when we talk about neural networks, we'll get this in a little bit later. We'll do time series first. But when we do neural networks, I'm going to talk about it more like what this looks like versus like I think the curriculum ends a little more the mathematical backbone, which I think is really important. And if you can dig into the mathematics and understand what's really going on, it's a really cool process. It's basically just linear algebra, which is kind of cool. But I'm going to kind of stray a little bit away from that just because I think it helps to give a little context of like, okay, what are these things doing? Like there's some mathematics stuff going on, but like, what does this really mean? And then we'll actually talk a little bit for the next couple from today and then onward. We'll kind of blend sections 41 and 42 and 40 all together. And I'm going to show you a little bit how to implement a neural network, the different parts of it, activations, optimizations. I think all those kind of come together versus like treating it as separate individual like lessons, if that makes sense. Okay, so just kind of know the format of our neural network is going to talk a little bit different. But today we're going to start talking with time series. So let's go into that. I'm going to share my screen. And I see Jessica and Akiva joined us, and Alvaro. Hey guys, hey everyone. And I'll make sure I share the right screen here. There we go. So there's time series. And sorry, I lost you guys too. There's my group of heads. Okay. So last time we talked about were like I call it like the basic models, right? White noise in random walk, right? And so I just wanted to quickly review this. I know like as I was kind of finishing up, I think people felt, I got the feeling that people were a little lost exactly what the difference between random walk was versus white noise. So the main difference between the two, and this will help us when we talk about autoregressive and moving average, because I think they have a similar analogy with each other. So the white noise model basically is just literally like randomness, right? It doesn't really, each new data point in the time series, right? Each date, right? Each data point is going to be a new time, like, so it's going to be in sequence, doesn't depend on the previous data point. So it's like if I told, to flip a coin, right? You flip heads, right? Next person, or let's say you say, okay, flip another coin and you flip tails, right? That tails was not reliant on the fact that you flipped heads prior, okay? So if you imagine like flipping heads and tails being a position of like 0 or 1, you basically would just be like 0, 1, 0, 1, 0, 1, 0, 1, right? There wouldn't be any difference. Where random walk would be equivalent of you still randomly flipping a coin. So let's say you flip your coin, it lands on heads, right? And then you flip your next coin, it lands on tails. But in this case, we have to say, okay, go ahead and walk a distance depending on what you flip. So let's say you flip heads is 1, tails is 0. So you flip heads, or you flip your coin, it lands on heads. You're going to walk like 1 meter out, right? And then if you get tails, you're going to stand still, right? So you would walk up 1, and then your next position would be basically staying exactly where you are. Then you flip again. Let's say you get like heads again. You walk up another meter. Let's say you land tails, 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 tails. You would stay where you are. So in this case, it's still random, but the position of where you are does rely on what you previously had. Does that make sense? Like at least a little bit of that difference between the two. And so I think I kind of was talking with another student, I think it was actually Andy, during a one-on-one, and he's kind of saying, can you go over this part? And I think we hit a good idea of this. So this right here is the white noise model right now, right? And you can kind of see, if I don't have it attached, right? So you can see the style. Actually, real quick, I'm just going to run this so that way I can play around with the data points. So you guys saw this code from last time, right? So All right, so I'm going to run this model right here. And note that instead of having it connected with like lines, right, I'm just having the dots, right? So you can see here, if I were to ask you connect the dots in series, it'd be a little tough to do, right? You can't really tell, like you can tell roughly where everything's like, oh, this stuff over here happened before this stuff over here. But like if I look really quickly at this point and this point, it's kind of, it's not really obvious like they're connected together and related to one another. Does that make sense? It seems more random. Does that make sense to people when I say random like that? Okay, and just to kind of show you like what it would look like if I did connect them, that's our time series, right? And this is where I think people get confused. It looks as if like, oh, you are moving along this line, but in reality, it really is just saying, oh, our thing was, I think, an average of 0. Yeah, our average was 0 and a standard deviation of 3. And basically that's what we're seeing, right? The distribution, but per time. Does that make sense to people? Okay. Now we look at our random walk model over here, and I'm just going to run this guy so I can make sure I have it. You can see instead here, it's like, okay, these points are all connected together, but I'm going to split this out so I can better manipulate this. If I put these little dot points again, right, you can see there's definitely like a pattern here, right? It's reliant where like the next point in position relies on where it was previously. So comparing this model to like this model over here, you can see there's this very, very like big difference. Does that make sense? Okay. So the important part basically is that like random walk, it's still random, but you remember where you were previously and you're just going to move from that spot versus just like, in some sense, it's like teleporting wherever you are. Okay. Cool. Thumbs up if that made more sense. Thumbs down, you're like, I still don't get it. Sideways. Okay, so mostly thumbs up, go up there. So cool. Any questions about those two things before we move on? No? All right. Awesome. So let's talk about ARMA, right? So autoregressive and moving average. So there's like, I will tell you again, like there's so much you can do with time series, right? Like people like study time series like exclusively for like months, you know, years, and like really get into details. We're not going to do that, right? If you're really interested in it, or if you're in an industry where like you're really like using a lot of time series, for example, finance, you know, stock markets and stuff like this, really care about time series, right? You kind of like to know what the next price of the price will be. But time series happens a lot in data science too, so it's kind of useful to know what's here. I will tell you, I am not an expert in time series. Like I don't claim to be. I like to be upfront with you guys, right? So know that like if you do have a question, I'll try my best to answer, but I'm not necessarily the best person to do it, right? But you know, we'll go through it. I'm kind of knowledgeable sometimes, so we'll see. All right, so autoregressive model. So what does this mean, this AR model? So I'm going to go back a little bit to this equation, and I kind of skipped over it. Like I pointed out last time, but didn't really like focus on it, was the equation for the random walk, right? So this is random walk with a drift, so just ignore the C. But you see right here, what this is saying, okay, the Y is the model itself, right? Like Y mean like the output. And so Y of T, so this time period, is equal to where you were previously, right? T minus 1. So wherever you were in the model previously, T minus 1, plus some epsilon, which is basically just random noise, right? So in this case, it's essentially the white noise model, but random noise at that specific time. So every time step, you have a new random noise, and you add that onto your previous point of like where you were previously. Does that make sense? Okay, so kind of keep that in your head a little bit when we talk about like ARMA. So what this looks like, if you look, it's like, hey, this is pretty close, right? Like, first of all, you see this part right here, like, hey, that's where we were previously. You recognize this. Hey, there's that white noise model, epsilon T, right? So this is kind of like, if you look at that, that's like the random walk, right? You can kind of see this point. The difference is that, first of all, there's this mu part. It's like, well, like I said over here on the random walk with a drift, that C is kind of like that extra, if you guys remember, it's kind of like, there's like either like the slope, like if you imagine a drunk person walking, right, there's like a slope, or there's some like wind pushing someone consistently off some level C, right? So that basically just shows like, oh, this is going to stay at this mu. There's always going to be this extra mu value, and this mu is just going to be a constant, you know, value, okay? And the biggest difference is this sigma, or not sigma, phi right here, or phi. It depends who you talk to, how you pronounce it. But the important part, this right here is some value that's going to basically emphasize how much does the previous point really matter to your next point. Does that make sense? So if you imagine if this phi is really, really big, that means that this value really matters, right? It has a large emphasis on the next point, at least in comparison to epsilon, assuming epsilon is some kind of scale. So that if this, if phi is really large compared to the scale, like the standard deviation of epsilon here, then we're going to have a lot more emphasis on this previous point. It looks like Jessica has a question or a comment.
Yeah, is phi okay? Because I think in the curriculum it says it's slope.
Mm-hmm.
Um, is it the slope of like the regression between yt and yt minus one, or is it like, okay, yeah, cool, that was my
Yeah,
question.
no, that's good. You can phrase it in a bunch of different ways, right? It's that if you looked at just like y of t minus 1 and y of t, right? The distance between those 2 points, if you got rid of epsilon, right? Because epsilon's some random noise, right? So it might kind of go up above. But if you took out the epsilon, it would just literally be the slope, right? From those 2 points. Of course, with epsilon, with the white noise model, it does kind of fluctuate a little bit. So it's always going to be slightly off of phi, unless you're extremely lucky of like epsilon of 0, right? Then it would be exactly phi. But if not, it would just be slightly off. But yeah, you can think about the slope as well.
Cool, thanks.
No problem. Yeah. And note this is a recursive definition, right? You would like iterate it over and over and over and again. And I showed last time how you can program this with cumulative sum, right? So you don't have to do like a for loop, which I don't know if the curriculum, I don't know if anyone recalls if the curriculum shows a for loop or if they use cum sum. I don't remember which, but cum sum tends to be a little more efficient because we're working with like matrices, right? Versus like doing for loops. If you can avoid for loops, it's a good day. Okay. All right. So anyway, so this phi right here basically really controls like what this looks like. Now note that if this is just equal to 1, we have the random walk with a drift, right? Of a drift of mu. So really, really easy. If we have phi is equal to 0, you will basically just have some constant, right? Which is its mean, which is basically just like it's going to be the same number, and then some epsilon white noise, right? So basically you just have the white noise model, right? With the mean of mu. Okay, does that make sense so far? The interesting stuff is when basically you don't have 0, right? So if you have greater than 1, I'm going to actually start with greater than 1. So greater than 1, if we do have 1, it depends, right, on what your previous point is. Or sorry, greater than 0. Greater than 0 is a positive number. It does depend at least at some point of where you were previously, right? So the previous points correlate with the past. We call that autocorrelation, right? It correlates with itself, autocorrelated. Makes sense, right, when you break it down that way. If phi is smaller than 0, it's a negative number, then it's kind of weird when you think about it. That means basically it's like, it still depends on the previous one, but it wants to flip over. So if let's say, for example, our y of t minus 1 is 10, right? And our phi is minus 1, then instantly when we get our new y of t, it's going to be minus 1 times 10, so minus 10, plus whatever random noise we have, maybe, you know, mu. We can treat mu as just 0 just to make it easy. But the point is basically you'll tend to have this kind of flip-flop up and down, up and down, up and down. So it still depends on the previous point, but the more negative it is, the larger that fluctuation. We call it like oscillation. So it looks like it's basically flip-flopping each time, oscillating over. Okay, does that make sense? Kind of breaking this part down? Okay, and I think that's really useful to think of it in this case of like the autoregressive model. Autoregressive meaning that it's just like, it depends on the previous point. Okay, and that's really what we're talking about. All right, so it kind of helps a little bit to kind of see like what happens when we start playing around with these numbers, like what actually happens. So I try to write this stuff down here and you can see a bunch of examples I have commented out. So we're just gonna try with a simple 0.1, right? So we have the average of 0, standard deviation of 4, number of points 100. This is just so we can get started off. So now that mu right here is going to be 0, right? So that we don't have to worry about that extra factor, but we could always throw it in there. Standard deviation of 4 is just so we can have like this white noise. I think I probably played with these numbers. 4 probably gives it like not too much fluctuation so we can see some differences. Oh, I'm sorry, I did put, sorry, I said this wrong. Average of 0 is for the sigma itself, is for white noise. So basically it's like, oh, it's gonna have 0 with a standard deviation of 4. So plus or minus, right? And again, standard deviation, right? We don't have to go over that. Like 67% of the time will be within one standard deviation plus or minus, okay? Mu is gonna be our average. So I guess I did put a mu here of 7. So that's gonna be kind of like your drift, right? And then phi is going to be 0.1. Okay, so we got these points defined. Let's say like we're just gonna basically create our time series. So we saw this before, we can create a date range starting from January 1st, 2015, completely arbitrary, going for 100 days, right? And then from epsilon, it's just going to be, we're going to generate a whole bunch of data points with the average of 0, standard deviation of 4, 100 different ones, right? So this will basically just give us 100 different points that follows that Gaussian normal curve, right? Okay, everyone following me so far? Cool, just breaking down this code. All right, so this one I think I actually put in the for loop. You could do this with cum sum, but I put for loop in here because I think it's a little bit easier to understand like previous point going through. So that's why I kind of did this. But note that if you were to code this, cum sum would probably be the better option, right? Because then it's vectorized. You can just do the math all at once, and NumPy loves that stuff. All right, so let's start off with y equals 0. So that's where we start off with. And then for e and epsilon, so we're going to have some random noise, right, called e. And the next point, y, right, is going to equal to the previous point, y, times phi, plus some noise, right, plus its that average mu, right? So that's just going to be a constant every single time. And then we're just going to append this into y. So you can already see this is not super efficient, but like it gets the job done so that for us to understand. And basically it's like, okay, we have a new y, we append it into our values, and then we start over with our new y with a new epsilon, or sorry, our updated y with a new epsilon. Okay, and just repeat that 100 times. Okay, make sense? Cool, all right. So, and then we're just gonna make a time series. So we make a nice series so we can actually plot some stuff. And let's just go ahead and run this guy. There we go. And just to kind of show you guys a little bit, well, I was gonna show you what time series, not really that important. It just, look, they're numbers. Ooh, okay, means nothing, right? So let's visualize it. So if we do our visualization now, we can actually go to plot this out and we can see what this looks like. So this right here is, let me just delete this guy. This right here is our autoregressive model with phi of 0.1, right? So you see that fluctuation, like it's not really fluctuating, but you can kind of see it kind of depends, but very weakly. If I put this 0, it would mean like it wouldn't have any relationship to the previous point. So if I do 0, you can see, I don't know, maybe it depends, but it's kind of random. A good way to plot this might be actually to plot it with this shape with like the dot points, but I think you get the point, right? It's kind of like, oh, it looks kind of like the white noise model. If we make it a stronger correlation like this, like 0.9, and note that doesn't take very much, you can see, oh, now we definitely see that random walkness, right? It's moving up. And note that it's moving up with mu as well. So if I put 0, this might be helpful. You can see it still depends a little bit. Like there's less randomness in that way. And if I put it really strong, I think this might be actually too strong. Let's see if I put like 2.9, you can start seeing, oh, basically every point depends and just shoots it up because basically like it adds up over time, right? Eventually it's just gonna keep going up, 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 right? So that's what's going on here. But I think the 0.9 is a good example. Everyone see like the relationship with that random walk, like what's going on? And then when I have that mu here with 7, it's like a random walk with a drift, so it's kind of going up there a little bit. Okay, cool. All right, so let's go then, let's try out if we have some kind of like oscillation, right? So let's start with like 0 or negative 0.5. So in this case, it's gonna flip-flop each time. So we should see that oscillation in there. And sure enough, when we do that, we can see there's a lot more oscillation going on there. Basically, you have this point right here, it's about like 6 or 7, right? And then it's gonna be negative, like negative a half. So it's like negative 2.5 plus, you know, whatever the mu is, plus whatever epsilon was. And you can see in this case, it's like negative like 2.5. So probably mu in was probably around like negative 7, right? It probably canceled out, but sorry, not mu, epsilon was negative 7. So they canceled each other out. Maybe I'll put this at 0 just to make things a little less complicated. Okay, so same idea. You see the oscillation. So we had the previous point about 1. It's going to be about negative half, right? So that'd be like negative 0.5, and then plus whatever epsilon is. In this case, it looks like it ended up being like about negative 1.5, but it's going to be about negative 2.5, right? So the point is that basically you'll see the oscillation. And the stronger, actually, the more negative this number is, the stronger that oscillation is going to be. And you can see here, now you can see with negative 0.9, there's a lot more oscillation. If I make this really extreme, like it's going to just look ridiculous. Like basically they're flopping each time is at this small part right here. I'm trying to think if I can actually, I'm not gonna do that. The problem is that it just happens to fluctuate right here, but you would see a bunch of fluctuations. But let's do something like 4. Nah, still too big, see? Wow, whatever happens on that end here. And that's just random chance, I think. So you can kind of see it, it's getting bigger and bigger, fluctuating over and over and over again, right? So I guess the reason why it blows up like this, right, is because it relies on the previous point. It's still multiplying it by negative, so it's going back and forth, negative, positive, but it's also getting bigger and bigger. Those fluctuations are getting larger and larger and larger. Does that make sense? I'm trying to find that good medium. There we go. We can see a little bit, like the oscillations get bigger and bigger and bigger and bigger until it basically blows up. Okay, cool. All right, everyone, makes sense to people? Thumbs up if that's good. Any questions at all about like what's going on here? No? The main thing about autoregressive is just know that we're basically saying how much weight the previous point actually matters. Okay. All right, so let's move on to moving average. So going back to moving average. So here, this is a little interesting. So it's kind of the same idea here. We still have epsilon, t, right, mu, all right, same stuff. We have a new constant, theta, and then we're gonna look at the previous point, but hold your horses for a second, right? You can see this guy right here, epsilon. Epsilon is actually not the previous model point, but the previous random noise point. Does that make sense? So this new point, what's it called, in the model, is not just dependent on whatever the new random point is, but also the previous random point, you know, with some weight of theta. Okay, so it's very similar to the autoregressive model, except instead of looking at the previous point in the model, we're looking at the previous random point. That makes sense? Okay, cool. All right. So, and you can see here basically the same idea. Epsilon equals 0. It's the white noise model, right? Nothing changes, right? It's just, or not, there's no extra factor in here from the previous point. With 0, or if theta is less than 0, it still oscillates, but it's going to oscillate based off of the random noise point. And then theta greater than 0, previous points are going to be strongly correlated with the past, right? So it's going to be closer and closer. So imagine essentially like double counting, right? So like if your previous point was like a epsilon of 2, right, and your theta is like 10, well, it's going to be really encouraged, like whatever that is. If it's your random point is positive, it's going to be really positive. If it's negative, it's going to be really negative, right? It's going to be hard for this epsilon t to really get out of that point or get out of that like extreme value. Okay, does that make sense to people? All right, cool. So again, it kind of helps just making some values. I'll keep these values. Oh, Alvaro, do you have a question or a comment? I see something go up.
Right now, we're only looking at 1 point behind, right?
That's right. It's just 1 point. And when we go talk about the ARMA model, we can combine many different points together. Good thing to point that out. Okay. So if I run this guy just with a negative, you can see that oscillation. Now note the oscillation is not going to be as strong as it was with the autoregressive model because we're not looking at the previous point, we're looking at the previous random point or random epsilon that's added to the point. Hopefully that makes sense. So basically the fluctuations, like you can almost think of it like the previous random point is just going to be like, oh, whatever that thing is, and it's going to encourage that more either in the negative direction or in the positive direction. So I think if I do 0.9, you'll still see oscillation here, but you can see the oscillation not very strong, like not as strong as the previous one. And I think on this one, this won't blow up as much. So there we go. You can see minus 1.9. Previously when we did minus 1.9, it really blew up, right? You can see like basically huge part, and that's because it depends on the previous one, but this is just the random noise. So it's not going to matter a huge amount. And in fact, if I probably put this, I don't know how I can do this without it blowing up too badly. You can see basically just the scale changes because it's not relying on the actual point in space, like for y of t, it's just the, or y of t minus 1, it's relying on what was the random noise of that. So it just means that the random noise from the previous point is going to matter the most. Does that make sense? Okay. And then you can see if it's positive, it just correlates positively. So you can see it should look a little like less, it should look a little more random than it did with the autoregressive model because we're looking at just the random points. Okay. Cool. All right, any questions on this? I think this is pretty, if you understand the first one with ARMA, I'm sorry, not ARMA, with AR, MA is usually a little easier to understand. Okay, cool. All right, so guess what we can do? We can put them together. Autoregressive moving average model, ARMA model, right? And there's other things you can do like ARMA and like SARIMA and all these different parts and stuff like that. But basically it's the same idea here where we combine them together and we can have both regression on the past values and also on the error values or epsilon values, right? Those they call them errors. I don't like call them errors because it makes it sound like they're wrong. It's just the randomness, right? The stuff that we don't have. Like we sometimes will say errors because we don't know what they are. So we call them errors because we like say, well, we know everything. So they're errors. I don't know. Anyway, so you can combine these together is that basically our y of t, right? We see that what that is, our epsilon, right? We're familiar. And then we basically just have these different points right here. Or sorry, not different points, or different weights. So we have phi or phi and theta, right? Basically saying how much does this matter? And as Alvera pointed out, we don't have to look at just of yt minus 1. We could look at previous points. So maybe like, for example, let's just say you're doing every single day and maybe 7 days ago, like every like Monday really matters and every Tuesday really matters. So like whatever thing you're looking at, maybe like what happened on that specific last Tuesday, so -7 really matters versus the previous day. Like maybe there's something about like that pattern that's happening on here. So you can have, for example, ARMA 2-1. So you can see here, for example, is that we're including all the parts for, what's it called? This one right here is the AR part, autoregressive. So we have phi of 2, phi of 1, and then we're basically putting a weight on t minus 2, t minus 1, and then 2 minus 1, or sorry, 2 comma 1. So 1 being the moving average part is going to much like this part. And we could have like 2 comma 2, 5 comma 4, you know, which would be like the 5 previous points of the moving average, or sorry, the autoregressive, and then 4 points for the, sorry, I'm losing my train of thought, moving average on that part, and then the other one's autoregressive. And note that they, basically, if you do this, it means that you're considering a lot more variables, right? Now we have, like just from this part, we have 1, 2, 3 different possible weights, right? We can kind of play around with to try to fine tune our model. If you put this 5 comma 5, you have 5 for the autoregressive, 5 for the moving average, and now you have all of those things. You have 10 different parameters to tweak and stuff like this. And in practice with most people's machines, if you try doing this the way you'd expect it, your computer usually can't handle it. Like I think people try to do more than 2, like I think people try to do more than 2-1. Like even 2-1 I think can be a stretch. Like 2-2 on like lots of people's computers just like ends up giving just garbage or just crashes out essentially because it's just too much for it to handle. But you could technically do it. Usually what you do is you're using like partial correlation function to see what are the things that actually matter the most. So the PACF talks about in the curriculum. You can use the PACF functions to figure out which of these, basically these time points, which of those actually matter. So maybe it's only every 7 days and something about that 7-day mark, you know. For example, if you're looking at month day-to-day model, day-to-day data, you're looking over like a year, maybe the 31st day of every month or like the first of the month or something is the thing that really matters. And there's the 15th day of the month that really matters or something like that. And you can look at those specific days now. Say, oh, every 15 days and every 1 day, stuff that really matters. We just look at, essentially, it would be like, you know, technically 31, 31, but you only care about like some of those weights and then everything else is 0. Does that make sense? Okay, so you can imagine this thing getting really, really big. And essentially what we do is just like, oh, cancel this out. Like, we don't need this part. We don't need this part. This stuff doesn't matter. Just these big parts. Okay, and that's usually what we do. One thing I'll note is that time series, as intense as it looks, really time series is really just linear regression on time. Like that's really what's going on. Essentially, you're trying to figure out what weights should we do, but really it's just linear regression. It's just, it's very specific to time itself where we're looking at previous points. Okay. All right. Yeah, that's kind of all the stuff I had for this part. I just wanted to kind of go through this because you might see it bump into, honestly, if it's something you're really interested in, there are plenty more texts and stuff you can go dig deep into. A lot more knowledgeable people than I am in it. But do you guys have any overall questions or something specific about how this works or anything like that? I can try to answer.
How about random weighted moving average? Are we going to cover that?
Random what?
Random weighted moving average.
Random weighted moving average. So the moving average part that you're talking about, like this guy right here, but random?
Yeah, well, it's what it's called, but it's where you're penalizing all of the older stuff so that it has less weight,
Okay.
right?
Yeah.
So that as you move along, the stuff from the past doesn't have as much influence as the stuff from the immediate past.
Mhm.
Right.
Yeah, you can. So this is more. I'm not familiar with that term. Maybe it exists. I just don't. I'm not as familiar in the field, right? But you can definitely play around with these weights. For example, if you have many, many weights, whether it's for autoregressive or the moving average, you can like exponentially increase them. It's like, okay, like the ones that are most recent, like T-1, are the highest weights, and then they decay out, right? So this, even though this is like I said, it's a constant right here, there's no reason why this constant can't be dictated from other equations of being like, oh, this is related to time. Of course, I'm no expert in it, but I'm thinking if you have it related to time, it also can be like probably folded it into like a more complicated model or more efficient model. But yeah, I wouldn't know specifics about that. But you definitely could say, oh, the one that matters the most. And that's where your PACF, if you do a partial oh my gosh, partial autocorrelation function, right? You can pull out saying what things actually matter the most. And that's why you tend to see that decay. If you guys looked at the PACF, you'll see that decay from like T-1, and then as you get further out, you would expect a decay because basically the past matters less, right? And that's where that PACF will actually give you these different it's called different weights. And if you look at your PACF and you see also a big spike where it's like decay, and then you see a big spike either in the positive or negative direction, you know that's probably a big thing that matters. So that's definitely going to be one to be put in your model at the very least. Does that make sense, Alvaro? I don't know if I really like
No, that's good.
satisfied. Like, yeah.
That's good.
I will pass it along. Definitely, like if you research more, I'm guarantee you'll learn much more than me pretty quickly. All right. Any other questions about this before moving on?
Are we going to cover like how you treat transactional data?
We won't specifically go through it on the curriculum and stuff like that, but if there's a specific thing you wanted to talk about, like, you know, there's not a reason why we can't go into it, especially for a project.
No,
But
we'll be talking about it. I guarantee you.
well, good. And I know there's a lot of stuff out there. Kaggle actually has a lot of great competitions that are ongoing all the time about transactional data,
Oh, I
and
know.
especially stock market. Yeah, they can get pretty intense if you start going in there. It's pretty cool. Again, I wish I could say I'm a better expert in time series and stuff like this. It's not something that I really came across until honestly, like within the past year. But that's just because of my background and what I've gone into. Okay, cool. All right, so any other things, or can I move on then to the next part, which will be neural networks? Sound pretty good? Okay,